All right, good morning, ladies and gentlemen. I'm very happy to have this opportunity to present some of our latest development at Park Systems. I'll start with a brief introduction, and I'll spend most of the time describing AFM technology innovation, including new AFM design, non-contact mode, fast imaging, and adaptive scan. And the last part, I'll describe about PinPoint Mode. Well, it was 1985 when the AFM was invented at Professor Kelvin Quaid's laboratory at Stanford University. And I was a graduate student in the lab, and I was one of the first students. And I thought, this is a great technology. It should not remain in a research lab. It should be commercialized. So I took a brave step of starting a startup in Silicon Valley, Park Scientific Instrument. That was in 1988. And indeed, Park Scientific was the first AFM company in the world. And then I sold the company to Soma Spectra and came back to Korea in 1997 and started my second venture, Park Systems. And our company grew successfully. So we went public in 2015. And we are listed in KOSDAQ, the Korea Stock Exchange. Since our IPO, we accelerated our growth. So our sales will reach about $40 million this year. And our stock price went from about 9,000 Korean won to now about 43,000 Korean won, and that is more than 4 or 5 times growth. And our market capitalization is about $260 million. Well, we must be doing something right, so I'll tell you what. Well, I think all of you know the principle of AFM, so I'll not go into detail. Basically, we scan the sample or probe. Here is the mouse, okay. Probe with a piezoelectric tube scanner and get local properties while scanning in X and Y directions. But this tube scanner, it is a very simple device to scan in sub-nanometer scale, but it has problems. So there are many drawbacks of a traditional AFM. Since the tube scanner relies on bending mode, it introduces background curvature and image distortion. And this tube scanner is slow in mechanical response. Another thing is tapping mode. You know, in tapping mode, tip touch the sample in oscillation cycle, so it makes the tip wear, and sometimes it modify or even damage the sample. And in general, AFM is not easy to use. You know, from the laser alignment and setting the numerous parameters, you know, beginner get overwhelmed how complex it is. So if you think about the essence of the imaging metrology tool, it should be accurate, and it should have enough throughput, and it should be easy to use. But conventional, traditional AFM does not meet any of these requirements. So it is quite miserable, or quite pity, I would say. So in order to address this problem, we developed the core AFM technology during the last 10 plus years at Park Systems. And first, we separated XY scanner from the G scanner, and we adopted a high-frequency G scanner. So we scanned the sample with the XY two-dimensional flexure scanner only in horizontal direction, and use another one-dimensional flexure scanner to move the probe only in vertical directions. So this is the actual design. So we use flexure hinges on both X, Y, and G scanner, and we use tagged piezo actuator. And this piezo actuator, stacked actuator, is very stiff and has high force, so it is much faster. G scanner has about 9 kilohertz resonance frequency. And XY scanner has a very good performance, very flat. This is raw data of optical flat image, 80 by 80 micrometer scan, and the peak-to-peak deviation is within 1 nanometer. And once it's calibrated, we could not see a considerable error in linearity and orthogonality. So the benefit is we have a flat XY scan system. It provides distortion-free imaging, and fast G-scanner allows non-contact mode. I mean, fast G-scanner alone is not the answer, but it's just a very prerequisite to make a non-contact mode working stably. So let me talk more detail about non-contact mode. The original idea of non-contact mode is vibrating, modulating the probe near its resonance frequency, and it disappears. And we find the frequency where the slope is maximum, so we drive at this frequency. And as the tip approaches the sample, the attractive force makes the resonance frequency downshift. So at this frequency, the amplitude drops by delta A. So now this is a new set point, and Z-Servo should maintain this amplitude while scanning in X and Y directions. But this tip sample interaction is not monotonic. This is where the attractive force starts to kick in, but as it gets too close, now the tip sample interaction is now changing to getting into the repulsive region. So actually the tapping mode starts to occur here, and due to the bouncing force, the amplitude increases suddenly and then reduce gradually. Even if we withdraw the tip, it does not go back to the non-contact mode. It remains in a contact mode, tapping mode for a while, and then drops. There is a hysteresis. So this bistability makes the Z-Servo quite challenging to follow the surface quite accurately. Once error signal exceed this non-contact mode region, it gets very unstable. So in order to avoid this problem, people found an easy solution. Instead of using on the right-hand side of resonance peak, if we use the left side of the resonance peak, then even with the attractive force, the amplitude increases instantly, and then it trends into tapping mode very smoothly. So there is no bistability once you use smaller frequency than the resonance peak. So this is a quick solution, and that's why non-tapping mode became very popular. It's very error-tolerating mode. But tapping mode has a problem, as I mentioned earlier. So the right solution is having a good controller to remain this tip sample interaction within this narrow region, typically plus minus 1 nanometer in amplitude or plus minus 2 nanometer in G. And for that, we need to have a very low noise system and fast Z-Servo. That's really important. This graph is actual experimental data, and you can see the system noise level is very low, and we use very small amplitude, about 10 nanometer or so. So once non-contact mode is working smoothly, then tip does not wear out. Compared to tapping mode, here the sample is chromium nitride T-check sample. So the tip gets blunt in just a few scans. It wears out very fast, and even with the peak force tapping, the tip wears out gradually over time, so you cannot tell what is the true roughness value. In non-contact mode, the estimated tip radius remains at 5 nanometer throughout 100 scans and few hundred scans, even few thousand scans. The tip does not wear out. This is a typical example of how non-contact mode is used in industrial application. In this case, we used one tip to scan this media, hard disk media sample, 800 times. And this is the first image, 800th image. The image looks about the same, and RMS roughness is about the same. And we also changed the tip. So now this is second tip, third tip, and fourth tip. And even with the tip is changed, the RMS roughness remains the same value, more or less. So that's how we achieve good repairability and reproducibility. And for that, we have to pre-screen the probe sharpness so that it meets within certain range. Another nice benefit of non-contact mode is the tip sample interaction can be sensed not only at the end of the tip, but also on the side of the tip. So as the probe scan and meet vertical walls, the side wall interaction can be sensed, and the Z-Servo withdraw the tip very fast, so it can climb over vertical walls. So this is an example. This sample has a narrow and deep trench, 3.7 micrometer deep, but our tip was able to reach to the bottom and climb up quite stably and repeatably. And this is a SEM image of the tip we use. This is a new tip, and this is the after taking 20 images, and the tip remains the same. So non-contact mode, preserve sharp tip. Okay, let me talk about fast imaging or high throughput scanning. Well, Bruker, they claim they have world's fastest AFM, and they claim they can scan fast with no loss of resolution. But this is certainly an overclaim. There is evidence in this video. If you look carefully, the forward scan and backward scan trace, line trace, do not match. So there must be a large amount of error. Well, in order to achieve fast scan, first we have to increase the Z-Servo bandwidth. For that, we need to increase the Z-scanner bandwidth and reduce the sensor response time constant and optimize the Z-Servo control. And then we can increase the X-scan rate within the Z-Servo capability. We analyzed the AFM Z-Servo loop. Basically, the sample height variation H is the input signal, and then Z-scanner motion is the output. And we want to make sure the Z follows as close as H. And we applied classical control theory. So the input H and output Z produce error signal E. E equals H minus Z. And this error signal is processed by sensor transfer function, controller transfer function, and system transfer function, and produce the Z. Here, the open loop transfer function is defined as Z over E, because this is the input and this is output, and that's basically PCF. While the closed loop transfer function, large H, is Z over H, because this is the input and this is the output. And if we substitute H as Z over H here, and then substitute to error signal as a Z over L, then we get this equation. With a simple algebra, we get the relationship between open loop transfer function L and closed loop transfer function H, as H equals L over 1 plus L. Now, our purpose is try to make closed loop transfer function behaves as a low pass filter, having a flat response to a certain level, and then gradual attenuation afterwards. And this can be achieved when open loop transfer function L is a simple integrator. If it is just a simple integrator A over S, then the H becomes low pass filter. So we want to make sure open loop transfer function looks more or less like this. Well, in the past, the G scanner was the bottleneck because tube scanner has about few hundred hertz resonance frequency. In our new NX system, G scanner has about 9 kilohertz resonance frequency. So now the bottleneck is the sensor response itself. In non-contact mode or tapping mode, the amplitude does not change instantly. If there is a sudden change in error signal, amplitude gradually get reduced with a time constant tau, which is 2 times quality factor over a resonance frequency, like this. So sensor response is behavior like a low pass filter with a cutoff frequency B about 600 hertz for typical non-contact cantilever, or about 2 kilohertz for fast high-frequency cantilever having a 2 megahertz resonance frequency. This is quite low, right? So forget about video rate AFM. Forget about scanning very fast. Practically, the speed limit of X scan is about 3 hertz in X with a standard cantilever, and it can go up to about 10 hertz with a high-frequency cantilever because we need about 100 data points back and forth. So if you scan faster than that, the image will be degraded, deteriorated very fast. And there are other transfer functions. System transfer function is dominated by the mechanical response of G-scanner. As I said, we have about 9 kilohertz resonance frequency, so that gives about 5 kilohertz bandwidth with 3 dB deviation. And the controller transfer function is composed of proportional gain, Kp, and integral gain, Ki, and it has a typical characteristic crossover transfer function, crossover frequency, which is Ki over Kp. Now, we want to make sure this L, open loop transfer function, which is a multiplication of those 3 to becomes like the simple integrator, and it becomes P over S when B equals omega C. If this numerator and denominator get be cancelled, so like this. So open loop transfer function is more or less like a linear integrator, except it's a kink. But this is not too bad because it's a log scale. This would not affect too much. And this is corresponding closed loop transfer function. So the pole zero matching, sensor pole and control zero should be matched. Then Z-Servo can follow the sample structure quite nicely. Whereas if the sensor pole and control zero does not match, the Z-Servo performance is not as good, as you can see in this simulation. After the pole zero matching, we have to adjust the overall gain so that the H should remain as close as 1 as much possible, but do not exceed. If the gain is too much so that it exceeds 1, it will oscillate. And if it is too low, it would not follow the sample surface very well. So this faster Z-Servo response, we should have a G-scanner resonant frequency as high as possible with a lower Q. If we can damp it effectively, maybe we can still use it at this frequency, at this gain. Okay, let me draw your attention to the relationship between scan speed and Z-Servo accuracy. I said open loop transfer function Z over E should be more or less linear integrator A over S. That means the topography signal Z is a time integration of error signal, right? If we differentiate it, dz over dt equals gain times error signal. dz over dt is nothing but G scanner speed. And that is, if the sample has a certain slope, dz over dt is sample slope times scan speed, right? So scan speed times slope equals gain times error. That means if you sample slope is fixed and we optimize the gain, and scan speed is directly proportional to error signal. So fast scanning inevitably increases the Z-Servo error. So we should limit the scan speed within the error level that we can tolerate. This is an example of our fast scan. We used high frequency cantilever having about 2 megahertz resonant frequency, and this is a 3 hertz, 5, and 9 hertz. The image looks more or less the same, and the forward and backwards line trace match pretty well. So this is a quite accurate fast scan without losing its image quality. In order to scan faster, we tried using small scanner, 10 micrometer XY scanner, which has a better X scan performance than standard scanner. And again, we used high frequency cantilever. Now we were able to scan up to 20 hertz, and it's not too bad. The image looks reasonably well because this Pentacene do not have that sharp feature, so we were able to image up to 20 hertz. Although there is a slight offset between forward and backward scan, it's not too bad because this is just a time delay. The image does not degrade that much. Okay, let me talk to you about adaptive scan. This adaptive scan is about automatic, intelligent scanning fast. Once we know the first line scan, we can estimate what the next what the next line will look like. Since we do not have any information of a new sample, we scan very conservatively for the first line, and once we get it, we can the next line will be similar to the previous line because the tip radius is typically about few nanometer, and that is usually similar to the line spacing. For example, if we scan 4 by 4 micrometer scan with 256 lines, then line spacing is 15 nanometer. So this is comparable. So for example, if you select 107th line profile, it's not too different from the next line, 108th line profile. So we can estimate what the next line will look like. So from the previous line profile, we take a derivative, calculate the slope, and then we apply low pass filter because the next line will be similar but not exactly the same as the previous line. And then we set the error margin, how much error we can tolerate. And then apply the equation I mentioned, scan speed times slope equals gain times error. So we can calculate scan rate within the error margin, and then we apply some clip. We we set maximum scan rate and minimum scan rate because we don't want to make too slow or too fast scan, and then next line will be scanned with this scan rate. So this is the result. This is the image, and this is a line profile. And for the flat region, we scan faster, and when the slope is large, we scan slow. So we scan fast, and then slow, and fast, and so on. Then the error signal will be remained within our set desired level. This is a scan rate image just for fun. And if we compare the adaptive scan with the fixed rate scan, we can see a good benefit. This adaptive scan took about 227 seconds to acquire this image. The forward and backwards line trace match pretty well. In order to get such accurate scan speed, result, we had to scan quite slowly, 0.2 Hertz, spanning over 1,000 seconds. Then you get similar match, good forward and backward scan match, but took much longer time. Well, if you scan 1 Hertz, then the forward and backward does not match as well. So we get both high accuracy scan with a fast, less time with the adaptive scan, right? Now, the user does not need to think about, well, should I scan at 2 Hertz or 3 Hertz? No. The user needs to set, do I need the best accuracy or higher throughput? If you are in draft mode, you can relax the error limit from 0.2 nanometer. It was a 0.2 nanometer. If you relax to 0.5, 1.5 nanometer, then we can scan even faster, right? The line trace, there is more error, like as you see here, but we can get still reasonably good image. So this is our new user interface. Our Smart Scan software has an auto mode, and this auto mode has a very simplified user interface. Please watch this 1-minute video.
Introducing the Park SmartScan AFM operating software from Park Systems. In the past, obtaining an AFM image was very complex. However, with our new software, Park SmartScan, now anyone can image a sample with just a few clicks of a mouse. First, you can find your area of interest by clicking your mouse. Then, enter your desired scan's pixel resolution, scan size, and its quality to speed ratio. Now just click on Image and your sample imaging will begin. SmartScan dynamically adjusts the speed based on the peaks and valleys of the sample, producing an optimum quality image. After the image is acquired, if you'd like to zoom to a specific area, just click it and click Image once again. Again, the software automatically calculates and uses the optimal scan speed and scan condition to generate the best AFM image. All done.
So as you can see, now taking a good AFM image is very simple, like a point-and-shoot camera. You know, you don't have to be an expert. Anyone can get a good AFM image very easily. The software algorithm will take care of all the rest. So now AFM has improved accuracy, has a higher throughput, and it's easy to use. So AFM is not what it used to be. Now let me talk about PinPoint Mode. This PinPoint Mode, basically we approach each point pixel by pixel and get FD curve, force distance curve. And from this force distance curve, we can measure stiffness and adhesion and so on. And on this approach speed and maximum contact force, dwell time, and retract speed, retract distance is all programmable. And this is possible with the state-of-the-art high-speed digital electronics combined with fast G scanner. And depending on the application and sample characteristic, whether it has a strong adhesion or no weak adhesion, or it has a hard material or soft material, we use different algorithm, JPK, JKP, JKR model, DMT model, and Hertzian model. You learned a good background information from Dr. Michael Kappel yesterday morning, so I'll not go any detail. And this is on some example. PDMS sample was imaged with a non-contact mode, large area, and then this is a zoomed in area. And now we used PinPoint Mode to get image of the same area. The image looks somewhat different because this is a non-contact mode and this is a contact mode. The sample is depressed, each pixel, so it looks slightly different, but we get all other mechanical properties, adhesion, modulus, and stiffness imaging. And this is another example. This is single coated graphene on rubber. And again, we get height, adhesion, stiffness, modulus, and deformation. This is a double coated graphene on rubber. So we get different images. This PinPoint mode is not only useful for mechanical characterization, but also electrical characterization. If you think about conductive AFM typically used in contact mode, but in contact mode, as the tip drags laterally, there is a lateral force that can damage or modify the sample, and the current image looks different between forward scan and backward scan. So this is not the best method. If you use tapping mode, you get better image, better topography, but the contact time is too short to get enough current data. PinPoint mode has both good topography and good current image with a good reproducibility. Piezoresponse force microscopy also get benefit with PinPoint mode. The similar thing happened. In this case, this annealed penanthrene is a very fragile material. So this lateral force or contact force can damage the penanthrene, but our PinPoint mode keep the sample intact. So we get much better piezo force microscopy imaging. Yeah, similar thing for the photoconductive AFM. Alex Weber group at Lawrence Berkeley National Laboratory, they used our AFM PinPoint mode to measure this photo-induced current with on a perovskite solar cell. Besides topography, they got short circuit current, open circuit voltage, and dark current. And they were able to measure spatially correlated heterogeneity. And they calculated efficiency indicator from those results. And they found there are high efficiency regions and low efficiency regions within the grains. And this result is important it provides an important clue how we can improve the efficiency of this perovskite solar cells. For the results experiment, they used glow box because the sample is can be modified with humidity and oxygen, and then they used photo current module with the laser module, and this result was very remarkable because with a typical photocurrent module, conductive AFM damages the sample due to the lateral force. This is another example of lithium-ion battery electrode. This is a cross-section of electrode. This is a topography, and with the PinPoint mode in vacuum, we get conductance image and corresponding resistance image, and also mechanical stiffness and adhesion image. Okay, so in summary, our business is growing fast and very successful. AFM performance has been greatly improved. With a separated XY scanner, we get flat XY scan that provide no sample distortion, and that contribute to accuracy. And high frequency G scanner enables fast Z-Servo that enables true non-contact mode, contributing accuracy. And Z-Servo optimization with high frequency cantilever, we can scan faster. And automatic parameter setting with adaptive scan provide ease of use. And PinPoint mode can precisely measure mechanical and electrical properties at nanometer scale. And Park AFM will continue to evolve into more precise, versatile, and user-friendly instrument. I present what we have today, but we also have next generation AFM on our drawing board. So you can expect more advanced version at some time later. Thank you very much for your attention.
So, yeah, thank you very much, Dr. Park, for sharing your innovations and giving us an overview on the products. Is there any questions? We're just in time, so there might be some time for questions from the audience. Oh.
Yeah, there are a couple.
Thank you for this very interesting talk and really the insight on the new developments of the measuring technique. I wonder, even though it's really established in the AFM community, that we stick to these maps as result being displayed. Do you plan in the software to use a little bit more statistic data exploitation tool so that you can provide distribution, statistic values of the materials directly within the software? So again, kind of topographic distribution where you can make matches and that to get a full coverage tool of the data analysis.
I don't get your question quite correctly. Do you have some specific example what you want to do?
You mostly display those maps, the 2D maps, and to get the information on this as information. You get export text files, but can you plot it another way, like a distribution function? So that's a little bit more working with the data to display, to make another visual appearance of the data.
I think it's related to kind of like an automatic data analyzation tool, which might be combined for...
Our industrial customer, semiconductor and hard disk manufacturer, they ask lots of data processing software because they need a number, not the image. So we develop many customized data processing routine. We do have lots of custom processing software, and also we can export our image or profile data to other MATLAB or Python or whatever software. So yeah, it is all doable. If you have something specific in mind, we can discuss.
Thank you. There are some more questions in the back.
To what extent, Stine Feide from Leuven University, to what extent do the developments that you have presented also have an impact if you do AFM imaging in liquids?
I think most of the technique is applicable. Flash scan and PinPoint mode also works very well in liquid, except the non-contact mode, because there is no clear boundary between tapping and non-contact mode in liquid. Our liquid operation can be benefited from this new development. Do you have some specific problems or?
Not really, it was a general question.
Okay.
Thank you.
Hi, thank you for the very nice talk. I would have a question regarding the high speed. When you were measuring at 20 Hz, you were saying that there was not good superimposition of the back and the forward and back trace, but it looked to me that they were simply shift and that in the reality the morphologies follow well. Could be applied any algorithm to just consider this and scan faster?
Yeah, if we apply some offset, we can look like it matches almost exactly the same, but that's not the purpose of the point. My point is, if we scan faster than 20 Hz, then the forward backward image line trace becomes different. It deviates because G-scanner cannot follow. The key point of my message is don't be fooled with the fast scan, video rate scan, or 100 Hz scan. I mean, that's a reckless speeding. I mean, you don't get the quality image. And to our experience, 20 Hz is about the maximum. And there are few example video. If you visit our website, there are fast scanning 20 Hz images, quite a few of them. But we don't recommend scanning too fast. I mean, 10 Hz is typically the speed limit, I would say. All right.
Okay, so I think this is it. And thank you again, Dr. Park, for the presentation.
Thank you.
And